Yeah. Okay. So anyway, so this proof sort of most of you have seen it in algebraic number theory, and those who haven't can just read through the notes, and or those who heard it is good. Okay. So that completes the proof of this theorem. And as so one consequence we already saw that B is a finite algebra, then B is integral over A. Second is the set of integral elements, set of elements of B which are integral over A, they actually form a ring. Yeah. So corollary is if you take x and y such that they are integral over A, then their sum and then their product are also integral over A. Yeah. So that's what one has to do to check that the set x in B such that x is integral over A is a ring. Okay, so it's closed under addition. Set of integral elements over A in some ring is closed under addition and multiplication. So this, by the way, so how does this follow, this corollary? So maybe it's a one-line proof, so I didn't write it here. Okay. So the proof is, AX is finite A module, and because X is integral over A, and similarly AXY, so Y is integral over A, so in particular it's integral over X. So this subring generated by X and Y, AXY is finite AX module. So that tells you that these two together implies that AXY is finite A module. So maybe this okay. So this is the statement here. Yeah. So this is the statement. B be a finite A algebra, C be a finite B algebra, then C is a finite A algebra. Yeah. So this maybe I'll put this as homework. So this is straightforward. Okay. Okay, so so that tells you that AXY is a finite A module, and in particular AXY is integral over A, hence X plus Y and X times Y, everything is integral over A. Okay, so this tells you that as a consequence, you see that set of all all elements of B which are integral over A is a ring, because it's closed under addition and multiplication. And this has a name. It is called the integral closure of A in B. Okay. Okay. So this homework I already talked about, and so finally, yeah. So let B be a finitely generated A algebra, which phi from A to B the structure map. So B is a finitely generated A algebra, means it comes with some structure map. Yeah? This ring homomorphism. If B is integral over phi A, then B is finite A algebra. Okay. So this is another consequence of this thing, and this in particular, this is the same statement which I stated earlier. Yeah. the converse of this thing. B is finitely generated A algebra, then B is integral implies B is finite A module. Yeah. In particular, so maybe in particular, if A contained in B and so some ring extension B finitely generated A algebra and B integral over A implies B a finite A algebra. B is a finite A algebra. Okay. So this, of course, again follows from same trick as this one. Yeah. So maybe I'll just write on the proof. So say B is generated by B1 to Bn as an A algebra. That means every element of B you can write in as a polynomial function of B1 to Bn. Yeah. And our objective is to show that every element in B you can write it as linear combination of some other elements, not necessarily the same BIs, but some other. Yeah, but we won't give you explicitly what those elements are. I will use this theorem, right? So B is generated by B1 to Bn as an A algebra, and B1 to Bn are integral over phi A by hypothesis, because B itself is integral over phi A. So every element in B is integral over phi A. So this implies yeah. So maybe for simplicity, I'll prove this second version. It's not even this is not bad, but so what happens is this implies that phi A by theorem. Okay, I'll do this. Yeah, phi A B1 is a finite phi A module. Yeah. But this is same as saying, I mean, the action of A on this subring of B is via phi. So this is same as saying phi A B1 or yeah, is a finite A module. And then, of course, this now, so here you are using that B1 is integral over. Again, so since B1 is integral over phi. Yeah. Now you use B2 is integral over phi A and hence over phi A adjoin B1. So if it's integral over a subring, it's going to be integral over a bigger ring as well. Yeah, because the same equation will work, same harmonic polynomial will work. So then, so maybe I'll write here, since B2 is integral phi A B1 B2, this subring is a finite phi A B1 module, and by this transitivity relation which we talked about, this implies phi a b1 b2 is a finite phi a module. And proceeding this way, we get this get phi of phi adjoint b1 to bn, which by the way is same as b. B is generated by b1 to bn precise as an A algebra precisely means this, yeah, and that every element of B is can be written as polynomial function of b1 to bn with coefficients in phi a. This is a finite phi a module equivalent, which implies B is a finite A module. Finite as an A module, yeah, finitely generated A module. I B is a finite A algebra. That is what finite A algebra is a ring, which is a ring extension, which is a finite module over the smaller ring. Okay, any questions? Any questions or comments? Okay, so okay, so these are so I haven't really done any examples, thinking that you may have seen it in number theory. Okay, so maybe yeah. So maybe we'll do some examples. I'll put up some examples as an exercise. So maybe one or two examples I should write it down here. Yeah? So examples of integral extension. So from number theory, you may have already seen these kind of examples. Yeah, so of course, one class of examples is finite field extension, or more generally, algebraic extension, or integral. So maybe z adjoins some, maybe root of some monic polynomial over z. So for instance, cube root of 3, square root of 3, or zi. So stuck. Or zi, or something like that, yeah. Or yeah, I mean, it could have fifth root of 2, and so on. And we saw many other example of finite z modules. Yeah, so all finite z modules are also elements of those are integral. Yeah. And
one second, but you cannot adjoin anything and say that it's integral, right? I mean, that's square root of 5, for example.
Square root of 5.
Yeah.
You can adjoin square root of, yeah, z adjoin square root of 5 is integral over z. is integral over Z, because square root of 5 satisfy
fine.
x square minus 5. Yeah. The polynomial x square minus 5. So you can't adjoin anything. For instance, you can't say Z adjoin square root of 1 over 2, 1 over square root 2. This is not integral. So maybe this is not integral over over Z. So if you put some fractions below, then it's not going to be integral. But yeah, you adjoin a root of a polynomial which has integer coefficient, root of a harmonic polynomial which has integer coefficient. By definition, it's integral. Yeah. The roots are integral, and hence the subring generated by it is integral. Okay, so these are and similarly over polynomial rings. Yeah. So localization and integral are sort of orthogonal in some sense. So if you are inverting something, it's not really going to be, it's less likely to be integral. Yeah. So yeah. So if you have some polynomial ring KXY Z or something like that, and you R is A is this, then of course and B is I don't know, A adjoin XYZ is already there, so W maybe mod W power 5 minus X square W plus Y is Y Z W cube plus X. Yeah, so something like this is going to be integral. Yeah, because it satisfies this monic polynomial. Yeah, so it's going to give you some integral extension of. So B is going to be B is integral over A. Or you can again do same thing, adjoin some square root, cube root, or some root of. So here we have adjoined a root of some monic polynomial with coefficients in it. Okay, so that's how you get integral extensions.
Okay. I have a question. What do you mean when you said localization is orthogonal to integral?
Meaning, if you do orthogonal in the sense it's a complement. So when you localize something, then it's not going to be integral. See, so of course, every element of the ring itself is integral. But as soon as if I invert something, Z to Z half, yeah. So this is not going to be integral, yeah. So how do you show this? So I mean, of course, we have seen that this is half. I mean, Z half is not finite Z module. So that is one way to see that this ring is not integral over Z. So in particular, half cannot be integral by that theorem. But I mean, if you try to write down its minimal polynomial, is polynomial. So the polynomial it satisfies is 2x minus 1. Yeah. But this is fx equals 2x minus 1. Then f of half is 0. Yeah. So and f is not monic. Yeah. But that doesn't mean so this is not enough justification. You have to work a little harder. Because this polynomial doesn't mean work doesn't mean that no polynomial work can work. So it may happen that theoretically it may happen that some other monic polynomial is satisfied by this number half, but in this case, I mean, there's something called normal rings, integrally closed rings, which I don't want to talk about right now. So when you are trying to invert the things, then it doesn't work. Yeah. So in particular, what I can
Yeah, I mean the localization is not integral extension of the ring. I mean that's what you
yeah.
mean. Okay. Yeah.
Yeah, and if you do some integral extension, and then it is usually there is something called normal rings. Yeah, so integral extensions are of normal rings. Um, it, so they are far away from. And they can't be in the fraction field. Yeah, so their intersection with the fraction field is the ring itself. Is something how.
This is what I got confused about. I mean, z square root of 5 is not normal, is what I wanted to say anyway.
Yeah, I understood. But I didn't want to
Yeah.
talk about
Yeah.
normal. Yeah. So I realized what you meant. Okay, so maybe I'll just state what integrally closed rings are, but unfortunately we won't do much. Yeah, so because it's not difficult to define it. An integral, maybe I'll define it for integral domain. An integral domain A is called integrally closed, or normal. So many people use normal, and some people use integrally closed. I don't know why, but at least I thought everyone used normal until I joined grad school. If
Yeah, we use the term integrally closed in number theory.
Yeah, maybe number theory is like that. Yeah, but algebraic geometers, at least of maybe previous generation, used to call it normal. Oh, so you have seen this, yeah? Fact of.
Yeah, we have.
So you know what normal integral domains are. So you know this result as well, that.
Yeah, we did not see the term normal. We know what is integrally closed.
Yeah, but did you see this result, that if alpha is integral over alpha is integral over a normal domain if and only if its minimal polynomial is monic?
Yeah, I think so.
Okay, so that's what I was telling you. So this is not difficult to prove. So I guess one can assign it as a homework, that if A is an integrally closed ring or a normal ring, then and B is a ring extension of A, and alpha is some element of B, then alpha is integral over A if and only if its minimal polynomial is monic. Okay. Polynomial of least degree, which is satisfied by this, is monic. Okay. Yeah. So. Okay. So that's enough examples and discussion. So maybe this was definition. So I mean, integrally closed, you have to learn in algebraic number theory. It's important. As Dedekind domains are precisely integrally closed number rings. Okay. Yeah, I don't want to make it further smaller. So sorry, you may have, but I hope you realize what the examples are. So anyway, examples are there. So let's just. So another fact you may have seen, I don't know, if A is contained in B, be an integral extension, and S is contained in a multiplicative subset, then S inverse B is. So S inverse B is not going to be integral over B or A, but it is integral over A. Okay. So have you seen this result? So this is, again, this is not in number theory, that is. So again, this is not, maybe in number theory, you may not have seen localization. Localization anyway you have seen earlier. So this is again not difficult. You just write down the equation, yeah. So any element in S inverse B looks like B over S, and B is integral, so you get some integral equation and you adjust denominators. Yeah? So this is going to be straight. Okay, so maybe I'll just write down the argument. If B over S be an element of S inverse B. Now B is B is integral over A. The integral over A implies B power n plus a n minus 1 B power n minus 1 up to A0 is 0 for some AIs in A. And then of course B over S power n. So you sort of divide by S power n, yeah. And an minus 1 over S B over S power n minus 1 plus A0 over S power n. So you adjust, yeah. So in the first term you bring one S out, in the second term you bring two S square out, and so on, is 0. So in S inverse B, and the coefficient here are now in S inverse A, yeah. This implies B over S is integral over S inverse A. Yeah, so sorry for where it's 0 is clear, yeah. So cramped up, but I guess this is not too bad, yeah.
Yeah, got it.
So and similarly, so there are some other results about integral extensions. Ordinarily I would have done some of them. So for instance, you can show, yeah. So so maybe yeah, so that's related to integrally closed rings. So you can show that UFD are integrally closed. So that gives you a lot of examples of integrally closed rings. Yeah. So every unique factorization domain. So polynomial ring in any number of variable over a field or integers is integrally closed. But there are examples of rings which are not integrally closed. Yeah. So I mean, you can just take something which is not a Dedekind domain. So, for instance, Z adjoin square root of 5, or yeah. So you can write down equations as well. So over polynomial ring, there are many examples. Meaning polynomial ring mod some. You can take some prime ideal, which I can write down, but maybe we'll do that later. Yeah. Okay. So so that's enough about integral extensions. So I wanted to get into Hilbert Nullstellensatz. Yeah. So hopefully, I don't know. Hopefully, we'll be able to complete this proof. So Hilbert Nullstellensatz, so there are many versions of it. So I've started with this algebraic version, and this essentially implies all the other version. So this is the base case, let's say, a base version, let's say. So let K be a field, A be a finitely generated K algebra, K x1 to xn, such that this algebra is a field. Yeah. A finitely generated K algebra is a field, then what you can conclude is that x1 to xn are algebraic over K. So note that if you have some sort of converse is always true, and it's trivial. Yeah. So if x1 to xn are algebraic over K and they are in some ambient domain, yeah, then of course the algebraic over the field K, then this is field, yeah, because you adjoin first guy, then we know that this is a field. So you get a finite field extension. In fact, it's a finite field extension. Yeah, so this from field theory. This note is from field theory. So the converse is trivial from field theory. So this you may have seen last time in your field theory class for one variable and then one element, and then you can just induct. So now for the converse. So converse is that as soon as you get that this is a field with finitely many elements, then x1 to xn must be algebraic over K. Okay, so for one variable, again, it follows from what you have seen in field theory. Yeah, so we'll prove this via induction on n and K any field. Yeah, so note that Kx1 is a field means means x1 must be algebraic over K, because 1 over x1 you can write like this, where as some polynomial in x1 with coefficients in K. And then, of course, x1 satisfies the monic polynomial, is integral over K, is algebraic over K, because you just multiply this equation by x1, and you get x1 power m plus 1 times something, and this K is a field, so you can divide by am to make it monic. Yeah, so x1 is integral over K. Okay, so n equals 1 case is straightforward. It's just same as saying that algebraic extensions are given. So algebraic field extensions are basically you get by adjoining polynomials, polynomial functions of those of that element. Now for the for a general case, so let's just assume it is true for n minus 1 elements adjoined to any field. So you look at this guy kx1 to xn. Yeah, so this is a field. Yeah, so in particular it contains the field kx1, k round bracket x1 adjoint x2 to xn. Yeah, and this is because I mean left hand side is a field. So every so whole of kx1, k round bracket x1 is contained in there, and then you can take polynomial in x2 to polynomial functions in x2 to xn. Yeah, so this inclusion follows from the fact that kx1 the left hand side is a field, and the right inclusion is always true. Yeah, so this is a field. So here kx1, I'm thinking of it as a field generated by k and x1. Okay, it's more like a notation. Any questions so far? Is this clear?
Yeah, it's clear.
Yeah, everyone? Okay. So now by induction hypothesis, applied with k equals kx1 and x2 to xn, so there are lesser number of elements. X2 to xn are algebraic over kx1 or integral over kx1. Yeah. So it's we haven't got that they are integral over k, but it's at least integral over kx1. So once we prove that x1 is integral over k, then we are done, right? Because then or algebraic over k, then of course kx1 is algebraic over k, and x2 to xn are algebraic over kx1, and everything will be done. Yeah. So okay, so maybe it comes here. Yeah. So enough to show that x1 is algebraic over k. So once we have x1 is algebraic over k, then x1, x2, xn are algebraic over kx1 by what we have concluded. Yeah. Now, yeah. So if x1 is not algebraic, it's going to be transcendental. Yeah. So that means x1 is like a polynomial ring. Yeah. And the problem with polynomial ring is it has too many primes. Yeah, so you can't. So the point is, you are saying that after adjoining x2 to xn, you have inverted everything in kx1. Yeah, and that can't happen in polynomial ring. So like even in the case from Z to Q, when we go from Z to Q, we know that Q is not a finitely generated Z algebra. Yeah, forget about module. Even as G algebra is not finitely generated. So similarly, Kx1, the fraction field of Kx1 cannot, if x1 is transcendental, cannot be generated. I mean, cannot be finitely generated k square bracket x1 algebra. Okay, or it's just adjoining some finitely many elements in some over-ring will not will not ensure that every element in kx1 is invertible. So that's roughly the idea, and we'll make this rigorous. Yeah. So consider this. So remember, x2 is algebraic over kx1. Yeah. So let's just take the minimal polynomial of x2 over this kx1, this field. So so it looks like something like this. Yeah, z power m plus bm minus 1 x1 cm minus 1 x1 z power m minus 1 plus so on, where bi's and ci's are in the polynomial ring kx1. Yeah, because every element of this field kx1 are fractions of fractions with elements in k square bracket x1. Yeah. So minimal polynomial will look something like this. So what we do is, if we invert these guys, yeah. So if we expand this ring kx1 by inverting c0 to cm minus 1, then what we would have concluded is x2 is algebraic, is integral over kx1 adjoint the inverses of ci's. Yeah. So that's what we are doing. C2 is integral over kx1 over a2x1, where a2 is the product of these ci's. Yeah. Because now the coefficients are in there. It satisfies this polynomial whose coefficients are in this ring. Is that okay? So we get that x2 is integral over this. So I'm trying to, if our objective was to just show that K round bracket x1 is not finitely generated K algebra, we would have done that directly. But we want to show that so x2 to xn are not in the fraction field, but it may be in some over field. Yeah. So we have to do some jugglery with this minimal polynomial. Okay, so we get this after adjoining 1 over a2x1, we still get that we get that x2 is integral over this guy. Yeah, and similarly we can find so there is nothing special about x2. X3 to xn are all algebraic over k round bracket x1. So we can find some polynomial in kx1 such that xi is integral over 1 over aix1. Yeah, so this should be x1. Maybe I should have just done x1 equals x. Okay. So hence what we get is that x2 to xn are integral over kx1 at comma 1 over ax1. Yeah, where a is the product of these polynomials. So it's just to write it in some shorthand. Yeah. It's not important that we write it in the shorthand. What is important is we are inverting something. Yeah, only finitely many of them. But inverting finitely many and inverting one is same, because we can just take the product of those which you want to invert. Okay, so we get that x2 to xn are integral over this this ring kx1 comma 1 over ax1. So just by inverting one guy, you can make all these things integral over this from algebra. So from algebraic over k round bracket x1, we got these are integral over k x1 adjoint some 1 over some polynomial. Yeah, that is what this minimal polynomial thing was for. Okay. But as I said, kx1 has infinitely many primes. Yeah, so that I hope you know. Yeah, prime elements. So I mean, it's same proof as Z, if you like. Or I mean, if k is infinite field, you can just take all the linear polynomials. If k is not infinite field, so if it's a finite field, then you have to do some work. But anyway, field theory, you have seen this, yeah. So this has infinitely many prime elements. Even a finite field adjoin a polynomial ring over a finite field has infinitely many primes. Yeah. So you can use the usual trick of prime number theorem as well. You know, you take, suppose there are only finitely many prime, you take the product of that and add 1. Yeah. So that must have a prime factor different from the list you have taken. So there are many ways of doing this. So now take px1 a prime which does not divide ax1. Yeah. So since a is some polynomial of some finite degree, you can always find a prime such that it does not divide ax1. Then of course, what we get is 1 over px1 is not contained in this ring kx1 x2 up to xn. Okay, and I should just throw in 1 over ax1 as well. Yeah, first note that 1 over px1 is in this guy because kx1 k round bracket x1 is in there. Yeah, so k round bracket x1 is contained in this. So 1 over px1 is this, since this is a field, if you like, since it is a field. But 1 over px1 is not integral over this. Yeah, because so as I said, inverting something is sort of far away from being integral. Yeah, so 1 over px1 is not integral over this, which is a contradiction, right? Because I mean, this field is integral over this kx1 x2 xn is integral over kx1 adjoint 1 over ax1. Yeah, because x2 to xn are integral over here. So that gives you a contradiction. Okay. Maybe I'll just say. So maybe I've written some justification for why 1 over px1 is not integral over this. But once you believe that, then this is a contradiction to x2 to xn integral over k x1 adjoint 1 over x1. Because then that will tell you that k x1 x2 xn is integral over this ring, but the whole thing is integral, but one element is not. Yeah. So why is 1 over px1 not integral over this? So as I said in the proof is sort of similar to the Q to Z case. Yeah. So there also I told you just complete the proof. So this is the idea. So suppose it is integral. 1 over px1 satisfies some monic polynomial. Yeah. So then it will be of this form, where so the leading coefficient, the coefficients are elements of this ring kx1 1 over ax1. Yeah, and how does elements of this ring look like? Some polynomial over ax1 power some element. Yeah, so this is localizing at ax1 essentially, the polynomial ring kx1. Yeah, so it looks like this. Now you just multiply by the product of all the denominators. Yeah, so you multiply by px1 power m, and you also multiply by I don't know, some you multiply by ax1 power some big number, so that this it clears out the denominator. Yeah, so where I is, let's say, maximum of I0 ym. This one. Okay, I should have used a darker pen. I is maximum. I've made it worse. And then you get that. So now, of course, px1 divides all the other term except the leading term. So px1 has to divide ax1 power I, but p is prime. Px1 is prime. So this happens in kx1 now. The polynomial ring kx1, yeah, is prime. So that tells you that it divides this contradiction to the choice of px1. Yeah. So that completes the proof of the algebraic version of Hilbert Nullstellensatz. Okay, so right in time, yeah. So are there any questions? So as I said, the intuitive idea is that there are too many primes in kx, and you can't invert all of them by just adjoining a few finitely many variables. That's the main main ingredient of this this proof. Okay, and then the rest is sort of so all this integral extensions are just a tool to do that. So this is the Hilbert Nullstellensatz is a very important theorem, and it has many proofs. So you can probably find fundamental theorem of algebra has many proofs, probably more proofs than any other theorem. Similarly, Hilbert Nullstellensatz has at least 5-6 proofs, or maybe more. I don't know. So there are many proofs of this this theorem, and but this is in some sense the simplest proof. Okay, sort of uses some minimal information. So there are some other tricky proofs and so on, but okay. So maybe next time we'll see more versions of Hilbert Nullstellensatz. And if you have any questions or comments, this is the right time to make them.
Okay, so maybe the idea is the following, that I mean, so k adjoin x1 to xn is a field over k. So yeah. I mean, k adjoin x1 to xn is something like 0 dimension because it's a field. But
yeah, but I mean, but 0 dimensional means field are always 0 dimensional. You mean 0 dimensional as a over k or something like that?
Yeah, over k.
No, that of course, if k is x1 is transcendental, then k adjoin round bracket x1 is also a field, and it's not. It has transcendence degree 1 over.
No, I mean not in terms of transcendence degree, but as a I mean in the geometric sense, it is a field, so it is 0 dimensional. That's what I mean. So, okay. but then it's integral over k adjoin k square bracket x1 localized at some I mean, so with some things inverted, but that's 1 dimensional as a ring, right?
Well, I mean, okay, so k, I mean, if x1 is integral, then of course.
Yeah, I mean, if it's not integral, then
Uh-huh.
k adjoint x1 with something's inverted, that has to be a one-dimensional ring, right? But you're integral over that, so you cannot have a zero-dimensional thing integral over one-dimensional thing because going up here.
Yeah. Yeah, sure. I mean, all this, yeah. So basically, I mean, x1, yeah. Yeah, maybe. Yeah, so maybe one can. There may be a proof via going up as well. Yeah. So, so anyway, so there are probably many proofs of this, and so yeah, possibly that way as well.
Yeah, thanks.
Any other questions or comments?